Hello and welcome to the introduction to data formats. Before we actually get to data formats, we need to talk about why is it necessary to talk about data formats at all. Why isn't it enough that, for instance, we create an application and this application contains a database or connects to a database which contains data, and that's it. That's what data is actually for, right? Well, this might work if you are a single developer, not working in a team, not communicating your data with other applications, and thinking about your application as your own, not to be shared with anyone. In that case, it is perfectly okay when you as a developer understand the data, know what is in the data, and your only worry in that case is that your application works and that your data is stored in maybe an efficient way, right? But if you think about the data this way, what happens if your application becomes deprecated and replaced by a newer version, or maybe a completely different application by another developer? If your data is connected to your application, then the other developer will have to collect the data from scratch, because your data was part of your application, and if your application is no longer desired or developed, and needs to be replaced, and the data was inside, then basically all the data is lost and needs to be collected again. So as you can see, this is one of the problems when developers think of data as a part of some particular application. There is a case which is especially dangerous for thinking this way, and that is public administration. And this is based on a real example that is happening with the Czech Ministry of Transportation, where actually the ministry had an application developed for management of public transport timetables. And this application contained the actual database, and the supplier supplied the application, and the ministry didn't have to take care of the data. They didn't have to process it and clean it. All that was done by the supplier. This worked okay until the ministry decided they wanted to access the data and publish it, let's say, on the web, so that there can be other applications that process public transport timetables, maybe in a better way than the original app. So in that case, they went to the supplier and they said, we want the data. We want the data about the timetables. Give it to us. And the supplier said, no, you only paid us to supply the app. Here is the app, but the data in the app is ours. So this was a mistake on the side of the ministry, because they didn't put it into the contract that the data collected about the timetables is actually theirs. So the data was still the supplier's, and the supplier was in a beneficial position because they were the only one with the access to the actual timetable data. So they were also the only ones with the application showing proper timetables, and no other application could be created because no one had access to the data. So this is beneficial for the supplier, but it is not beneficial to anyone else. And in addition, if the ministry would want to switch to another supplier for processing of timetable data, they would be in what's called a vendor lock, because they couldn't do that They cannot do that unless they want to lose all the data with the app as well. So this is also an undesirable state of things. Another case when thinking of data as part of software will become a problem is when you want to share the data with someone else, maybe some other developer creating another application. So if it is just the two of you, then you will definitely be able to negotiate the interface. So you'll say to the other developer, I'll send you the data like this, and the other developer will say, okay, can you adjust this a little bit? And you'll say yes, and they'll say, yeah, that's fine. And they will do the same with their data. So somehow you contact the other developer and you negotiate the interface using which you will exchange data. So again, this works fine when it is just the two of you. But then other developers can come and say, okay, I want to exchange data with you as well. And the more developers come, the more it will be impossible to actually negotiate a data format or an interface for data exchange with each of them. So they will all become unhappy because of this. So this is another bad effect of thinking about data as an integral part of an application. So instead, what we are going to do is we are going to think about data independent of applications. So if we are going to develop an application which works with data, we will first take a look at the data, what is in there, what entities are represented there, and design that correctly, and think about the representations of the data and all this. And only then we will create applications which work with the data specified in this way. What happens then is that we have the data. The data has a clear specification, clear rules of how it looks like, and each developer of each application interested in working with the data can read the specification and create their application using this one specification, which makes everyone happy because they do not need to negotiate with other developers, and they have a clear specification they can lean on. Okay, so when we think about data as independent from applications, is that it? Is that all we need to think about? Well, no, because the fact that we agree on a common specification of data doesn't mean that this specification is correct. We may, for instance, choose a wrong data format for our use case. This actually happens quite a lot. You'll see a lot of cases where, for instance, tabular data, so data which looks like a table, it has rows and columns, so it's two-dimensional, is represented in a data format which is hierarchical, such as XML or JSON, which are data formats we will go through in this course. So this is a choice of an improper format for a given use case. Other problems can arise when the developers do not know the specifications or do not adhere to them properly. So then maybe the JSON format is invalid or the XML is not valid. And it causes a problem because one application, one system produces the data, another system wants to consume the data, but it just doesn't work. And now the problem is that one of them or maybe both of them do not follow the specification. But for instance, in business, the fact who actually didn't follow the specification is quite crucial, because the one that is not compliant with the specification will have to pay for it and adjust their software. So this is why it is necessary to have a specification so that it is possible to clearly say who is not following it, so that they then need to adjust their system and pay for the change. Okay, so this was a brief introduction to the problems that arise when not enough attention is given to data and data formats. Here are the points of this course. The main points of this course are to give you an overview of common data formats, their specifications, and tools that are there for working with those data formats, and also to give you an overview of use cases in which those data formats are appropriate to use. Another point of this course is actually to give you the ability to choose a proper format for a given use case, and the ability to think about data independently of applications, and not only in one way, but at various levels of abstraction. And here we have the conceptual level, where we talk just about what the data is about, what entities of the real world are represented, how they are connected, what properties they have, and that's it. We won't talk about technologies on that level. But then when we agree on what the data we are talking about is actually about, then we can go one level down and talk at the logical level of view of data, which is how the data that we know looks like factually. So we know what is in the data. So how do we represent the data in a specific technology or format? This is what we will be dealing with at the logical level. And then there is the physical level. So when we know what is in the data and we know which format or technology we want to use, we also need to know how, using that technology, format, or data model, the data is actually represented in storage, on a disk, in the cloud, but how the data looks like in a file. We'll start with the conceptual view on data, because this one is independent of any particular format or technology, and still we can talk quite a lot about what is in our data. And also notice that this will be independent of also any application that might work with the data. We'll just talk about data. And on the conceptual level, we'll create something called a conceptual domain model. As I already mentioned, it is independent of any particular technology or representation. And using that model, once created, we can answer the questions like what real-world entities are described in the data, what are their properties, and how they are connected. The advantage of the conceptual model is that it can be discussed with non-IT personnel, so businessmen and businesswomen and other people not familiar with data and data formats and files and computers at all, and they still will understand what the data is about, and you as a developer can actually negotiate with them if that what is modeled is actually representing the real world accurately. I'll show you how to create a conceptual model based on an example of a data catalog. A data catalog is a catalog like any other, only containing data to be, let's say, downloaded, and the data will be described using properties like what is a name of a data set, its textual description, maybe how often it is updated, where it can be downloaded, and under what terms it can be used, and so on. But we will get to that. Let's start with a very simple thing, and we will use UML Class Diagrams, which is one of two notations commonly used for conceptual modeling. The other one is ER model. And you might have seen this in your database system course already. But we will need this in our course as well. So let's just illustrate conceptual modeling on an example. As I was saying, we will use UML class diagrams for that. And we'll start with our first class named catalog. So a class in UML class diagrams is represented as a rectangle with a name. So here we have a class called catalog. A class in conceptual modeling basically says there are things in real world which are of this type. So using this class, I'm saying in the real world there are some catalogs, and this is how I will represent them. This is their type. So all the catalogs in the real world I am talking about are of this one type called catalog. Right. My catalog will have a title, a description, and a home page. So those are attributes. Basically, this says that each instance of a catalog, each catalog, has these three properties. Now let's add another class. So we already talked about a catalog, and now we'll add a contact point. So a contact point represents a point where you can contact someone. So the contact point has a name, for instance, the official contact point, and an email. So again, this is represented as a UML class, and it means that there are many contact points, each of this type, and each has a name and an email. So now we have catalogs and we have contact points. Let's connect them. We will connect them using something called an association. An association connects classes, and basically it says that an instance of a catalog is connected to an instance of a contact point. You may notice that the association has a name so that we can refer to it, and it is connected to the classes via association ends. There are two of them in this example. One of them is connected to the class catalog, and the other is connected to the class contact point. Now, there are multiplicities for each association end. As you can see, for the catalog association end, we have 0 to many. The star represents many. And at the contact point association end, we have 0 to 1. This means that one instance of a catalog may or may not be connected to up to one instance of contact point. So basically, a catalog either has or has not a contact point. On the other hand, one instance of a contact point can be connected via this association to none or up to many instances of a catalog. So one contact point can serve as a contact point to many catalogs. Right, let's add another class. So now we have a catalog and a contact point, and we'll add a data set into the catalog. As I told earlier, we are talking about data catalogs here, so it makes sense that in the catalog we'll have a data set. So again, we'll add a class. The data set will have a title and description, and it will be connected to the catalog using the dataset association. Now both ends of this association have the 0 to many multiplicity, which means that one dataset can belong to many data catalogs, and one data catalog can contain many datasets. Also, the dataset can be standalone, not belong to any catalog, and the catalog can be empty, not containing any datasets. Now, the dataset will be described using more attributes. We'll have keywords, we'll have documentation, specification, and some resolutions of the dataset. And what's new here regarding attributes is that even attributes can have multiplicities. So here, keywords is not mandatory, and there can be many keywords for each instance of a dataset. The same goes for the specification. On the other hand, each dataset has a documentation. Now, as you may have noticed, there are two more associations in our conceptual model. There is the contact point association, another contact point association, now connecting a dataset and a contact point. Now, let's focus on this association for a bit, because we now have a cycle here. We have a class catalog, which is connected to a contact point, and we have dataset, which belongs to the catalog, and the dataset is also connected to a contact point. An important thing to mention here is that this cycle does not imply that the contact point connected to a catalog needs to be the same instance as the contact point connected to a dataset which belongs to that catalog. Those can be completely different instances. They do not have to be the same. The conceptual model does not speak anything about what a specific instance has connected to what. So it may be that the catalog has a contact point number 1, and the catalog has a dataset which has contact point number 2, which is completely different. Or it might happen that the contact point of the dataset actually is the same instance of contact point as the catalog has, but both options are possible, and none is more likely to happen than the other. Okay, let's add some more associations. So there is nothing new regarding the conceptual model. So we'll add a data theme, a frequency, spatial coverage, URL concept. We don't have to actually understand what the individual classes mean here, because I'm using those just to illustrate the conceptual modeling, not to teach you about this particular data domain. One thing that I didn't mention and is actually new a bit is the part of association, because it goes from the dataset class into the dataset class. So it has the same class at both association ends. But the association ends have different multiplicities. And therefore, if we were to name the association ends, we could distinguish the direction through which the association is used. Basically, what this conceptual model wants to say is that a dataset can be part of another dataset, but just one, and the other way around, a dataset can have many parts. Right, let's add another class, and that is distribution. Now, we talked about dataset as describing some data, but the dataset actually does not talk about where to actually get the data, where to download it, where to access it. That is what distribution is about, and each dataset may have many distributions. What is interesting and new here is that when we take a look at the distribution association, it says, via its multiplicity, that a distribution always belongs just to one and exactly one dataset. So that's the multiplicity 1 to 1. It means that when a distribution exists, it always has a dataset connected and exactly one. Right, and a distribution can be described by some attributes like download URL, access URL, and so on, and a title maybe. And also it is connected to other entities like a specific media type or specific file format. So for instance, we want to say it's an Excel file, and we'll say it by stating the file format, which in this case, as you may have noticed, is actually also mandatory and always one for the distribution. And each distribution may be, or has to be in this case, described by terms of use, which tell you what you can and cannot do with the data. For instance, who is the author of the data, if the data is copyrighted, and so on. Again, the actual content of the data is not the point here. We are just illustrating how data can be modeled on a conceptual level. So let's add one more and final class, and that's a data service, which represents data accessible via an API, where you can query to get the data described by the dataset. For those interested in what we are actually talking about here, this is a conceptual model of a check specification saying how to describe data sets and distributions, how to describe data catalogs. So if you have a data catalog somewhere in the Czech Republic, you should be following this specification. And the specification was not created entirely by people in the Czech Republic. It is based on a European specification called DCAT AP, which is based in turn on a worldwide specification called DCAT, where DCAT stands for Data Catalog. And the DCAT specification is published by the W3C company, which is the World Wide Web Consortium, as a recommendation, so it is a web standard. We will talk about this, the standardizations and so on, later in this lecture. What is important to say is that all the time I was talking about what is in the data, what are the entities, what are the attributes, and how they are connected to other entities. I didn't mention once any particular representation of the data. I just talked about what is in the data. So as you can see, you do not need to know XML, JSON, or CSV to be able to talk about data, for instance, with some people in business or some non-IT people. Right, so we talked about what is in the data, and now we need to go one level down in the view of the data, and we need to talk about data models, data formats, and data schemas. It is also important to know the difference between a data model, a data format, and a data schema. Let's start with a data model. So when we will be talking about data models, we will be talking about the shapes of the data that we'll want to achieve and the tools that we'll have for it. For instance, we will talk about the resource description framework model, which basically structures data as nodes of a graph, where each node is identified by an IRI, which is an identifier that you may know as URL also. And those nodes are connected. When a node is connected to another, it will be read as a simple statement in English. For instance, there is an employee called Anne, which would be represented by the lower left node connected to the rectangle node at the bottom. So this is one of the data models. It's a graph and it's very granular. it is not the only graph data model. There are others. We will also talk about the labeled property graph model. The labeled property graph model also structures data as a graph. However, it's a little bit different graph because here we also have nodes as things, but they are not identified by URLs. They are just labeled. And each node has a label and a set of properties. For instance, we have Dan, who is labeled as a person and has a name and has age. And then we have edges which connect those nodes to other nodes, and those edges are also labeled, and they also have properties like Dan knows Steve since the 1st of March of 2021, and so on. So on the left, in the RDF data model, edges are also labeled, but they do not have any properties. On the right, they have properties. So then when we have our conceptual model and we are deciding how to actually structure what is in the data using a given model, we need to think about, on the right with the labeled property graph, what will be the properties of the edges, what will be the labels of the edges, what will be the properties of the nodes, what will be the types of the nodes. And with RDF, we'll have to think about how we will identify the nodes and how the individual nodes will be connected and so on. So both are graph data models. Both will lead to to data shaped as graphs, but each of them is slightly different in what it allows you to do and how it allows you to build the graph and what the individual properties or components of the graph can contain. But the graph data model or the graph data models are, of course, not the only data models available. We can also think about structuring our data as a hierarchy or as a tree, which is a specific kind of graph. It has a root, and in the case of the document object model that you may know already from, for instance, HTML, and which will be also used in XML later, we have a different structure. We need to think about what will be the root element. For instance, here it will be an element containing coffee shops, and the element will have attributes and other sub-elements. Maybe the attributes will have textual values or values as numbers and so on. So we'll have to think about how to structure our data described by the conceptual model in a form of a tree like this. Or maybe we'll decide that we want to represent the data at the logical level as JSON, which is both a format and a model. Let's talk about JSON as a model here. So JSON has arrays and objects have property value pairs. So for instance, here we have a top level array which contains an object which has a property name with a value place, and it has a property employees with a value which is also an array, and the array again has object and so on. So this is a different hierarchy or tree type that we might choose as a data model for our data. And again, this is not the hierarchical and the graph data models are not the only ones. We also have the traditional relational model where we have tables with rows and columns, and those values in those tables may reference values in other tables. And here we'll think about how do we represent our data according to the conceptual model so that it fits into tables, rows, and columns. So again, I have not talked about how the data looks like in a file or in storage. I just talked about how the data will be shaped what tools do we have to represent the data. So on the conceptual level, we describe what is in the data, how the entities are connected, and so on. On the logical level, we decide how the data is shaped and what tools are there to represent the data. And this brings us to the physical level and physical view of data, where we finally talk about data formats. So for a given data model, we will talk about how can we serialize it or save it into a file or send it over the network. For instance, for the RDF graph model, there are 7 standard serializations and 1 non-standard serialization. Some of them are text-based, some of them are binary. For the property graph data model, there are many different representations in files. For the document object model, there is XML and HTML. For JSON, there is JSON, but we can also represent the JSON model in XML. So there is that. And of course, there is the relational data model. So we can represent relational data as CSV files or as SQL dumps and so on. We will talk about those data formats throughout this course. So here it is just an overview of what is ahead. Now, when we have a specific data representation, typically there is also something called a data schema. A data schema is a document containing annotations explaining what is in the actual data instance and constraints allowing us to validate the data instance, to say whether it adheres to a specific format or if there are any errors in it, and to specify those annotations and constraints, there are schema languages for each of those data formats. So for instance, we have the CSV on the web language for describing schemas for CSV files. We have JSON schema language for describing annotations and constraints for JSON files. And we have the XML schema language for the same purpose in XML. And you may notice that for specific data formats, there are multiple schema languages to choose from. The bold ones are the ones that we will cover in this course. Now, when we specify the constraints, we may also look at it as specifying a sub-language, so a language used within the format itself. The generic formats like CSV, JSON, and XML, which basically say how to structure the data into a file, but they do not tell you, for instance, in the case of CSVs, how to name the columns and what the columns mean, and in case of XML, how to name the elements and attributes and what they mean. They just say that an element looks like this and an attribute looks like this. So for this reason, sometimes those languages are, or those formats are called meta formats, because by themselves they do not define any specific language. They just pose as a host format, and only together with a schema you can say that you have a data format for a specific use case. For instance, to be specific, JSON specifies that you have data structured as arrays and objects and values, nothing more. But GeoJSON is a specific set of properties or keys that you are supposed to use in the JSON to represent geodata. So for instance, some polygons on a map or something like that. And the GeoJSON language tells you how to use the JSON host format or the meta format so that it is interoperable, so that others understand it the same way you mean it. For CSV, such an example would be the General Transit Feed Specification, GTFS, which is used, for instance, in Google Maps when you are trying to find your connection, for instance, from metro to tram and from tram to another tram and so on. You are trying to get to your destination and you search for this in Google Maps. What it does is that it uses data which is published by the Prague Public Transport Company using the GTFS language or format, which actually internally is CSV based. So it uses CSV as a host format. The same goes for XML, where the examples are SVG, which is a format used for vector graphics, Atom or RSS, which are formats used for news feeds, or maybe you know Office OpenXML files, which are used by Microsoft Office programs. And for RDF, we have already seen as an example of conceptual modeling the DCAT vocabulary, which specifies what URIs are to be used to identify what in RDF to represent a data catalog. And another format specification can be mentioned schema.org, which allows you to use RDF to annotate web pages, for instance, to allow Google to search for them better. Since we are going to talk about data formats a lot, let's have a look at some of the generic properties that we may use to describe them. And let's start with what is an open format and what is a closed format. An open format is such a data format that its specification is available on the web and freely accessible to anyone, with no limitation on its usage, which means that anyone who wants to can create an application according to the specification and therefore work with the data using that format. So clearly, examples of the open formats are XML, JSON, CSV, RDF serializations. Those have their specifications on the web, but the more interesting situation is with the specific formats. So the fact that XML, JSON, CSV, and RDF are open means that you can create your own languages and your own applications which work with data in XML, JSON, CSV, and so on. But it also means that you can use XML, JSON, CSV, and so on as a base for your own data format, like GeoJSON, SVG, and so on. SVG and GeoJSON, as I already mentioned, are specifications for vector graphics and geodata, and those as well are open, so you can find that specification online. You can create your own application according to that specification so that you can work with data in that format, and no one prohibits you from that, and no one places any obligations on your application. On the other hand, when you have a closed format, it has the following properties. You may not have access to the specification at all, so you'll see the application producing some data, but you will not understand the file itself. You will not be able to understand what is in it because you won't have the specification. Or maybe you will get access to the specification only after payment, or maybe you will have to register as a user of the data format so that you can use it legally. Or maybe when you create a application consuming data according to the data format, you may need to undergo a certification process or something like that, so an obligation. Example of such a format is RailML, which is an XML-based format. It has a specification available online. It is used for representation of rail-related data, so timetables, but also rail topologies and so on. And if you want to create an application and say that you are consuming or you are working with RailML data, you need to undergo certification. Otherwise, you cannot claim that. So this is an example of a closed format because you cannot use it freely. You need to do something or pay something to be able to use it. So this is the difference between open and closed formats. And quite naturally, we will focus on open formats in this course. Another term used to describe formats is machine readability. And this one is quite interesting because there are various opinions on machine readability. For instance, someone may say that all files are machine readable because all files are in the end read by machines. They are stored in storage which is read by a machine, so inherently all files need to be machine readable. Well, of course this is not true. The second part is because in the end all files are read by machines, but machine readability is not about this. Another statement that you might come across is that open formats like CSV, XML, JSON, or some RDF standardization, or maybe the Excel OpenOffice format is machine readable, and that's it, nothing more. Well, let's take a look at some of those formats and let's think about whether this statement does hold, right? So is it true that when we use open formats like CSV or XML and JSON, the files are machine readable? Well, how about this? On the left, we have a CSV file. So this is your first look at the CSV format, but does it look machine readable? Does it look very nice? On the right, you also have a CSV file. And again, let's ask ourselves, does it look machine readable? Well, let's take a look at another example. And yes, this example is in Czech, but it actually doesn't matter. Just take a look at it. Do you think that this file is machine readable? And see that most of the data is actually included at the end as a huge unreadable string. Let me give you another hint. Here we have two instances of data in Excel. So on the left we have some cities and changes in the numbers of inhabitants and changes in their budgets. Those are purely imaginary. I created this just to illustrate what the machine readability term might actually be related to. Well, one of them is machine readable, the other is not. What does it mean? How is it possible? Well, note that both are Excel files. And if I say that one is machine readable and the other is not, it means that actually machine readability is not a property of a specific format, because we have here two files using the same data format and one is machine readable and one is not. If you take a closer look, you'll see that on the left we have a table which is structured using rows and columns as a natural table would be structured. And that's okay. That's the machine readable file. On the right, we have an Excel file which is not machine readable. And why is that? Well, if you take a closer look, in that Excel file, we actually have a screenshot of a table. So technically, we have an image which is stored in the Excel file. So we have an Excel file in both instances, but if we want to, for instance, sum the budget changes, the three rows, if we want to sum them, when we have the data on the left, it will be easy. When we have the data on the right, we have just an image, not an actual table. Even though it is stored as an Excel file, it will not be that easy because we'll have to basically rewrite what is in the image into the table, and then we can sum it. And this actually is exactly the difference between machine readable format and machine unreadable format. it does not depend on the format itself. It is a property of a specific data instance, which means a specific file. So machine readable file is a file where the data format is used as it is supposed to be used, and it is easily processed by an appropriate application. So, for instance, when we have tabular data, like we had with the Excel, if by the appropriate application, which for tabular data Excel is quite an appropriate application, if the data is processed easily, then the data is machine readable. If it is not processed easily, then it is not machine readable. Now with Excel, there is one danger, because machine readability and the processability of the data should be by applications, so by scripts and so on. In Excel, you may easily have some data which is easily processed only by Excel and not by other applications, in which case we basically talk about machine unreadable Excel file. Other examples of machine readable files are, well, we already had tabular data, right? So machine readable table is a table which correctly uses rows, columns, and cells so that they are easily processed. So no encoded images, no encoded JSON files in a cell of a CSV table, and so on. For textual data, again, a machine readable format for textual data will give you access to individual characters without or with ease, without any hassle, especially without needing to use optical character recognition. This is again the case with some, for instance, PDF files. Some of them are just images, some of them actually contain the textual data. So that is the difference between machine readable and machine unreadable file. Another property of a data format is whether it is binary or text-based. And again, I'll start with a quote. So recently at a state exam, a student told me that a binary format means that the file is stored as ones and zeros. Well, that's of course not the proper definition, because also text-based files are of course stored as ones and zeros. How else would a file be stored in a computer, or at least nowadays? So the true difference is that binary files, the structure is described on a bit-by-bit level. So you can say that the first 3 bits represent something and the next 4 bits represent something else. And how can you spot a binary file? Well, it's quite easy, because when you open it in a text editor, you will not be able to read it, because text-based files are readable by humans and you can open them in a text editor. When you have a binary file, you can view it by a so-called hex editor, which will basically show you the individual bytes of the file shown as 2-digit hexadecimal numbers. So on the left, we have a PNG file, which is an image, and it is opened in a hex editor in Visual Studio Code. So as you can see, you see the individual bytes as numbers, but the decoded text is not readable by humans. On the other hand, we have a text-based file which contains text which is readable by humans. But again, if you take a look at the hexadecimal representation of the file, you can again see the individual bytes. So even text-based files are stored, of course, as zeros and ones, as numbers, which can be represented or read byte by byte. But in the case of text files, in those bytes, there is encoded a human readable text. And the text is encoded there using something called a character encoding, which we'll talk about momentarily. Another property of text-based files is that typically the characters are on lines. So a text-based file is structured using lines, typically. It's not always like that, but typically yes. Also worth mentioning is that sometimes binary files are simply called non-text files. So whatever does not have an encoded text is a binary file. So let's talk about character encoding. And let's start with the simplest one, which is US-ASCII. US-ASCII uses 7 bits, so not even a whole byte, 7 bits to represent one character. And on the right hand side, you can see a representation on a punch card. So on each row, you have the 7 bits. Each bit is either set to 1 or 0. And on the right side, you have what character is encoded using that bit combination. So what is on the punch card is actually the word Wikipedia and a new line encoded using the US-ASCII encoding. And the US-ASCII encoding is defined by a code chart, which is on the left. So for instance, with the W, which is the first character on the punch card, we can see that it is represented by 1010. So we can see in the US-ASCII code chart that we need to start, or we can search the column header, and we start with 101, which is the third column from the end with a number 5. And after 101, we have 0111. So we search the rows and we find 0111. And in the 101 column, the number 5 column, on that row, we see the W. So this is how characters are encoded into ones and zeros in text-based files. And this is the most the simplest of encodings, US-ASCII. Of course, we can see that this encoding will not be enough, for instance, to represent the Czech language or Japanese or Vietnamese and so on. For that we have other encodings, but for representation of English and some special characters, this is enough. But because I mentioned that one of the key properties of text-based files is that it is structured into lines, it is quite important to mention or to note how the lines are separated in a text file. So there are many ways or many characters, or many ways of how to represent a new line. The end of line is called a new line. And for instance, in each of the commonly used operating systems, the new lines by default are represented in a different way. So for instance, in Unix-based systems or on Mac OS, a new line is represented by a single character called a line feed. That is also the case on the right in Visual Studio Code. When you open a text-based file, in the bottom you can see the new line representation used. In this case, it is line feed or LF. Again, in the ASCII table, you can see that there is the line feed character represented as 0001010. The line feed character is often escaped as \n as a new line. And on systems like Microsoft Windows, the new line is represented by a pair of characters, which is carriage return and line feed. So there are 2 characters in Windows representing the new line, and those are often enough escaped as \r as carriage return and \n as line feed. Right. If you wonder why are those characters named this way, carriage return and line feed, then know that the origin lies in typewriters, where you would type your line of text, and when you reach the end, you would return the carriage and you would feed the paper so that you are actually on another line. So from that, those two symbols made it into the ASCII table. Now I mentioned that US-ASCII is not sufficient for other than English languages. That is true. The encoding which actually is used on the web and with data exchange is UTF-8, which is a Unicode encoding, and of course it is not enough to represent the individual characters using just 7 bits, because those are what 7 bits allows us. We've seen with US-ASCII. Here each character is represented by 1 to 4 bytes, so up to 32 bits per character. What is worth mentioning is that UTF-8 is backwards compatible with US-ASCII. So if you have characters from the English alphabet, you will have them represented using 1 byte, which is 8 bits, where the 7 bits are exactly the same as in US-ASCII. Also, one property of UTF-8, the Unicode encoding, is that the most frequently used characters use the least bytes. So the US-ASCII characters use just 1 byte. If you add languages like European languages, they will take 2 bytes. And when, for instance, you take emojis, which are also which can also be encoded using UTF-8 Unicode, those take 4 bytes to encode. So this is a brief introduction to UTF-8, the Unicode encoding, which is actually used on the web in files today. One character, one special character, or maybe a special sequence of bytes worth mentioning when talking about Unicode is BOM, the byte order mark. Because UTF-8 is not the only Unicode encoding. There are others like UTF-16, UTF-32, and so on. It was decided, or it started being used, that at the beginning of each file there would be a magic number. And that magic number, the byte order mark, would indicate which type of Unicode encoding was used and what was the byte order for multi-byte encodings. In Principles of Computers, you may have already learned about big endian and little endian as different ordering of multi-byte values. So for instance, here UTF-16, big endian has a different byte order mark than little endian, so that it is clear from this byte order mark when a text file starts which encoding type is used and whether it is big endian or little endian. Well, since in data exchange basically only UTF-8 remains in use, the variant that is being used actually is the variant without a byte order mark. So byte order mark is not used with UTF-8 on the web. You may find a file which uses it, and then it looks like what you can see on the bottom of the slide, and that is you see the first 3 bytes are EF, BB, BF, which corresponds to the UTF-8 encoding. And when you see the decoded text, it actually decodes the first 3 characters as some weird characters, and then the actual text starts. So this is so that you know that there is something like a byte order mark, and you might come across it, but the rule here is that it is not being used when data is shared or sent over the network. And I mentioned just 2 encodings, US-ASCII and UTF-8, but there are many, many more encodings you might come across, but actually they were superseded by UTF-8. What you might come across in the Czech Republic is ISO 8859-2 or Windows 1250, which are two legacy encodings, sometimes used in older systems. But as I said, nowadays UTF-8 is used everywhere because it satisfies all possible use cases. Now that we introduced data formats and maybe some basic properties of data formats, and also we know how text-based formats look like on the byte level, we need to take a step back and take a look at standardization, which means why do we need standards and who creates the standards and how. The first question is, why do we need standards? Well, we need standards for interoperability reasons, so that when, for instance, one type of data, let's say your tax reports are to be turned in, so that they are all turned in the same format regardless of who sent them, because otherwise, when the situation would be like in the image, when each data producer produces their data in a different way, shaped differently using different data format, it would be a hell to work with all those data, even though conceptually they represent the same thing. So in the situation, in the image on the slide, it might as well be that all those data files represented by the different shapes actually contain conceptually the same data, for instance, data catalogs. However, because they are using different data models and different data formats, it is impossible to work with all the data as if they were from one source, which is what interoperability is all about. But also, standards are necessary for business, because when something goes wrong with data exchange, it needs to be clear who is wrong, if it is the data producer or the data consumer, because it is a big difference when someone has to pay a developer to fix something, whether it is the producer or the consumer. So to avoid all these situations, standards are necessary. Now, one may say that standardization is costly because you need to contact all the stakeholders and you need to write the specifications and documents, and then you need to teach the individual users how to use the specification and how to produce the data. But take a look at this. One specification for each dataset or each domain or each conceptual model, one specification needs to be created, so that takes some work. And each provider needs to learn the specification, each provider needs to adjust, for instance, the data publication process, and each consumer needs to learn that specification to be able to process the data from the consumers, from the providers. However, without standardization, when the data is not interoperable, the interoperability is low, actually this is more expensive, because now the data provider, when they are sending the data, they still need to create a specification so that they know how to shape the data to send. So each provider creates their own specification. And again, each provider needs to learn the specification and adjust their data publication processes. The difference is that there are as many specifications as there are providers. And now the consumers need to learn all the specifications to be able to work with the data, not just one. So actually, the lack of standardization is costlier than when we standardize data formats. So now that we know that standardization is necessary and why, let's take a look at some of the organizations that create those standards. So one of the organizations that creates mainly Internet standards is the Internet Engineering Task Force, IETF. They are part of, or they are governed by the Internet Society organization. I will talk about in a bit. But Internet Engineering Task Force is a standards organization founded in 1986, and initially it was supported by the US federal government to create standards. So now it is, as I said, under ISOC, the Internet Society. The participants in the IETF are volunteers, so anyone can participate voluntarily without pay in any of the IETF working groups. A working group is an organizational unit of the IETF, and each working group has a topic, has a chairperson, a charter saying on what problem they will focus on and when they will deliver a standard, for instance. And this working group is open for all, so anyone interested can be part of the process. Now, when a working group finishes working on a specific task, for instance, here in the slide you can see how an RFC, a request for comment document for the JSON format looks like. And this actually is an Internet standard now. Well, when the working group thinks that they have it, they pass the RFC to the Internet Engineering Steering Group, IESG, for a final technical review, and they may say, yes, this is ready to be an Internet standard, and publish it as an Internet standard grade RFC, which is what you can see in the slide for JSON, or at least a header of it. Now, I mentioned ISOC and Internet Society. This one was founded later in 1992, and its motto is to promote the open development, evolution, and use of Internet for the benefit of all people throughout the world. So, as you can see from the motto, it is more on a political level, so deals with the political issues regarding Internet, and leaves the technical standardization to the Internet Engineering Task Force. But you may see RFCs, request for comments, documents from other bodies than just the Internet Engineering Task Force. Now, these standards are Internet related. So they deal with the TCP/IP protocol or for instance, the JSON data format. But there is a difference between Internet, which is the network, and the web, which is basically an ecosystem using the Internet to create a web of interlinked documents. And the web and the web standards are managed by the World Wide Web Consortium, which was founded in 1994 by Tim Berners-Lee, who is the inventor of the web, but not the Internet. The Internet, the network, predates the web by quite a lot. So the web is, or was basically the web of interlinked human readable and writable documents using the Internet. And the W3C issues recommendations, which are then de facto web standards. And you might already know some of them, like HTML or CSS for specifying the styles of web pages, or RDF, which we'll talk about, and XML, which we'll also talk about, or RSS, which is the newsfeed format, and so on. Many more recommendations. What is important is that there is a process to how a proposal becomes a W3C recommendation, and it has 4 main stages. First, there is again a working group which collects some ideas of how to approach a certain problem. And they write up a draft of a specification. And then it might become a working draft when the general public is given access to the draft to issue comments. So then there is a time period when the working draft lives, gets changed a lot as the feedback from the community comes. And then when the editor thinks that the specification solves the given problem that the working group was dealing with, they request that this working draft becomes a candidate recommendation. When this is approved, a candidate recommendation is given to developers, and the developers basically provide feedback on how this recommendation is implementable. So how well it will be implementable in existing tools, or how well new tools can be implemented to actually be compliant with the recommendation. When there are such a tools found, or enough feedback from developers is collected, the specification goes into the proposed recommendation state, and when it collects independent implementations and there are no more big problems with the specification is tested both theoretically and practically by implementation. Is tested both theoretically and practically by implementations. It is upgraded to a W3C recommendation, which basically says, and now the rest of you people implementing something similar on the web, use this as a standard. Now, anyone can request to become a member of the W3C. It is a paid membership, so typically members are universities, businesses, government, or non-profit organizations, and the employees of those organizations are then members of the working groups responsible for the individual recommendations. Now, besides those standards organizations, there is another one called Icann, which is an acronym for Internet Corporation for Assigned Names and Numbers. And this organization manages IANA, Internet Assigned Numbers Authority, which basically is the authority for different lists of things that make the internet work. For instance, they are responsible for managing the IP address space, both IPv4 and IPv6. So they are those who divide the address space into chunks and provide those chunks to continents and countries and individual providers and so on. They also number the autonomous systems on the internet. If you do not know what an autonomous system is, it doesn't matter right now, and you will hear about that on a computer networks course. They also manage the root zone in DNS, the domain name system. So they basically say where are the domain name servers for .com domains and country domains like CZ and so on. And for us, the most interesting part will be that they also manage media types. And media types are actually format specifications. So a media type has a identifier. You may already know, for instance, text/HTML is the media type for HTML. And the document describing the HTML format is registered with IANA and becomes part of the media type registry. So the media type registry is a list. You can click on the link in the slide and see it. The list of all registered data formats and their identifiers used when those formats are used on the web. And that's not all. There is another standards organization called ECMA. Now, note that all the previous organizations were US-based, United States-based, and ECMA is actually EU-based. So its HQ, headquarters, is in Switzerland. It was founded in 1961. It is also membership-based. So again, companies, universities, and so on pay to be parts of ECMA. And there are some standards that are quite widely used. For instance, the C# language is standardized by ECMA, or the ECMAScript language, which is based on JavaScript, or for instance, JSON is ECMA standard 404, or the Office OpenXML standard. Now, you may have noticed that there is a JSON standard by ECMA, and before I showed you a JSON standard by the IATF as an RFC. This is quite common, actually, that one standardization organization publishes a standard such as JSON, and then another standards organization publishes their own standard for the same thing. Sometimes they are compatible, sometimes they are not, but that is the state of things. And that was an overview of the standards organizations that we will come across when talking about standards. And another thing we need to say before we actually go and see specific standards is how the standards are written. And one interesting standard which says how standards are written is RFC 2119, which specifies or defines the exact meaning of some words like must, required, shall, and so on when used in specifications. So for instance, it says that when a specification contains the word must, then this is an absolute requirement of the specification, and when someone does not comply with the thing that is a must, then they are not compliant with the specification. On the other hand, there is a word should, or that something is recommended, and this means that it should be adhered to, so you should implement that in your application unless there is a valid reason and you understand the implications when you ignore this part of the specification which is recommended or introduced by the word should. So this is a first actual RFC that I presented to you, RFC 2119, which says or defines words used in other RFCs and specifications. And this convention is actually used also in W3C recommendations and so on. So it is a good one to know. Another example of an RFC that introduces a technique that is used in other RFCs and standards is the ABNF, which is a augmented Backus-Naur form, which specifies a simple grammar, which allows you to say or to specify other grammars. For instance, JSON language can be defined by a grammar expressed in ABNF. We don't have time to go into details, but it is quite intuitive, and when you'll see it, you'll know that it is it. And if you'll need it, you know that the definition is in RFC 5234. Now, you may have noticed that I am talking about the web a lot. And that is because when we are talking about data format, the most common use case nowadays is that you need to serialize your data in a stream or in a file and send it over the web. That's why web and data formats nowadays are closely connected. And when we talk about data on the web, we need to talk about identifiers which are used on the web and in the data. You see, to identify a data item independently of a data format used, you may use or you may want to use one of those. And you probably already know a URL and you use it in your everyday life. When you share a web page or a link to something, you share a URL. But it is important to understand that there are different kinds of identifiers, and they mean different things, even though they may look the same. So let's start with the easiest one, which is URI, Uniform Resource Identifier. What you see in the example, in the top part of the example, is a URI. It is an identifier which syntactically looks familiar, right? So there is a scheme, authority, path, a query, and a fragment part of the URI. Now, you might ask why this is not a URL, because it looks the same. Well, it is true, it looks the same, but the function is different. You see, with a URI, all you get is an identifier. And what is the purpose or the function of an identifier? Well, it is to distinguish different things and to indicate when we talk about the same thing, by the identifier being the same. So a URI, a Uniform Resource Identifier, does exactly that. It serves as an identifier which syntactically looks like what you see in the slide. Especially this means, in contrast with URL, that you cannot expect the URI to serve as a locator, because if it would be a URL. And what the difference is? Well, if you take a URI and place it into your browser and hit enter, nothing needs to happen because it's just an identifier. But if you expect the URI to work in a browser, which means it can be also used to locate the resource identified by the URI, to get it, for instance, using the HTTP protocol, then you add another function to it. You need it identifies a resource and it helps you locate it as well. In that case, it is a URL, a Uniform Resource Locator. With URI, you cannot expect it to work. With URL, you expect it to work like this. Well, then there is a URN, Uniform Resource Name. A URN is what you see in the bottom part of the example. A URN is a URI, but it's a URI which uses the URN scheme, and then it has a structure which is split into a namespace and then some namespace specific identifiers. And the namespaces are managed by another IANA registry. So like there is a registry for media types, there is also an IANA registry for URN namespaces. And you can register your own unique namespace there. And the URN serves for unique naming of things, nothing more, just naming of things. So it is not a URL, it is a type of URI with the URN scheme and the URN namespace registry. And that leaves us with IRI, Internationalized Resource Identifier. Now, Internationalized Resource Identifier is a URI which allows you to use Unicode encoding in the path part. So URI actually allows you to only use US-ASCII in the path part. IRI allows you to use Unicode. So these are all examples of URIs. So they are all in ASCII. They use different schemes like FTP, HTTP, LDAP, mail-to, and so on. An interesting thing is that there is a URI scheme for telephone numbers, for instance. You probably know the URI scheme for mail addresses, so that's the mail-to. So all those are URIs. The most prominent ones are the HTTP-based URIs because they often serve also as URLs and you use them in your everyday life in your web browsers. Now, here is IRI, which is nowadays commonly used for identification of everything. And as I mentioned, IRIs allow you to use Unicode in the path part of the identifier. So examples of URIs are on the top left. Now, the problem with URIs that you might come across is that some technologies do not work with them. For instance, HTTP requires URIs, even though the newer HTTP versions are well aware of the existence of URIs. They still require you to use URIs. Part of the URI standard is the encoding of URIs into URIs, which is called a percent encoding. And it works like this. If your URI contains a character which is not from the US-ASCII encoding, remember that Unicode is backwards compatible with US-ASCII. So when you go outside of US-ASCII, Unicode is up to 4 bytes. Each byte gets encoded into a percent sign and the hexadecimal 2-digit number representing that byte. So for instance, the poop symbol, which is an emoji, which is 4 bytes, is represented by those 4% encoded bytes. When an URI goes through the percent encoding, it looks like the examples on the bottom of the slide. So they are not readable, but they are valid URIs using US-ASCII and usable in technologies that require them. Note that when you see an URI in your web browser, such as Google Chrome, when you copy it, it gets copied as a URI, so it doesn't look readable. There is a link from the slide to a Chrome plugin which allows you to copy the Unicode readable URI from your browser on one click. So you may use that if you ever feel the need. Now there is another RFC connected to Unicode in URIs, and that is RFC 3492 called Punycode. You see, Unicode in the path part was covered by URIs and percent encoding. However, you may also use Unicode with domain names, but there, again, some technologies like DNS do not work with Unicode in domain names. So for them, the Unicode representation needs to be encoded again. But here, percent encoding is not used. Instead, another encoding, Punycode, is used. So, for instance, you can see the example on the left in Unicode, on the right in Punycode. And the Punycode representation is actually what you then register with your DNS provider. Okay, so that was introduction to identification. We will use URIs to identify everything. For instance, in the Resource Description Framework, RDF, data model. But URIs are nowadays used even in CSVs, JSON, XML, and so on. So that's why we started with them. And the final thing I want to tell you today is that even though there are different data formats, and we will talk about different data formats like RDF syntaxes, XML, JSON, and CSV, in all those data formats, data types are from the same scheme, which is defined by the XML schema language. So it means that a Boolean value looks the same or should look the same in JSON, in CSV, in XML, and in RDF syntaxes. The same goes for numbers, integers, decimal numbers, that you can see that it's a decimal number because it has a dot. For floating point numbers because they have exponents, and the same representation, which is based on ISO 8601 standard, applies to dates, times, date times, and date times with time zones. Okay, so that's all for today. That is the introduction to data formats, and we'll continue next time with some specific data models and data formats.